Gogo no, Agime no, Anashite wa, kan Nakai-san desu.
Muito obrigado.
So, maybe I will speak English if you prefer. So Nakai, Professor Nakai is from university, very interesting. You know that water is very important for two things. For beer, first, when you want to make beer, you need very good water, and also for tea. And there is a tea water university, which is Osha no Mizu. Mizu is water, Osha is tea, so Osha no Mizu University. So it's University of the Water for Tea. And it's university for women, which is also interesting fact that Japan is one of the last countries where there exists women university, but Nakai professor is professor in this university. So, but I have to give the title. Oh, excuse me, I have to say something well, not much, very important. Excuse me, very important before that. Many people are leaving, some people are leaving today or tomorrow morning, and they did not register to Sueli, to the secretary, in order to organize return, to organize a van to bring you to airport. So can you register to Sueli, to the secretary, to say when you return, and it's even if you don't need maybe, in order to know, people who need some van to bring them to the airport. Okay, so now, most important is to give the title for Professor Nakai, which is Web Geometry of Solutions of First Order Odes. Okay, thank you.
Yeah, thank you. 3 web. Is 3 foliations. Okay, so definition is very simple. So, of course, so if we call D web, so then it means defoliations. And so in these talks, so always, so we talk web structure on the C2. Okay, and also germ. And the first example of a very curious 3 web structure is the linear one. Given 3 points, okay, and take pencil of lines passing through those 3 points, okay, and inside or possibly outside. So we get the 3 foliations. Okay, and here what we can do, we can see a very beautiful structure. And okay, so fixed point. This is very, very elementary. So okay, so here we see triangle. And given point, okay, there are 3 lines passing through it. So say let this is x1 and this is y1, okay, x2, y2, and x3 and y3. Okay, of course we know. So this is very elementary thing in junior or high school, okay, mathematics. And so here we see relation x1 over y1 times x2 over y2 times x3 over y3 equal 1. Okay. So let's think about the dual, okay, dual picture. So here for one point, for each point we have one lines. Okay, this is the dual picture, but still we have the triangle. Okay, and this point inside corresponds to lines. Okay. And this line passes through this point. It means it corresponds to this intersection point. Okay? So this is our triangle, and this is the line. Okay? This is x, say x dual, and x stands for this point. Okay? And here, and here, and here, we have three intersection points. Okay? By introducing some coordinates on this dual line, this is, say L1, and this is L2 and L3. So introducing some good coordinate on it. So we have some relation, say A, B, and C. Okay, so here I suppose A stands for some coordinate, B coordinate, and C stands for coordinate. So then on this dual picture, we have also the relation A, B, C equal, say 1. Okay, so these theorems are called, I don't know. So this is the universal name, Melanès or whichever. So in projective geometry, this is sometimes called the ZAK, Z-A-K theorem. Okay, and so everything is well known, but non-trivial thing is, and the group structure is behind. One can define group structure on the three-line configuration. Okay, so say on the L three-line configuration, say union of L1, L2, and L3. Okay, the group structure is C star cross Z3. Okay. And say the relation is defined by, just forget about one, numerical one, and assume this stands for point, okay? And this is point, point, and this is abstract multiplication. So this relation must be, one should be E, identity in this group, okay? So by this relation, we can define group structure. Okay, so, and if, so this is a good way to understand everything, but so to understand geometrically, to look at the geometry more carefully, so that put this pencil, the base point, to the infinitely far from our place, okay? So then pencil becomes line, parallel lines, and put this point, that point, okay, to infinity in this direction. So then formation becomes horizontal lines. And the third one, and go to somewhere else, very far from here. So then, okay, everything becomes parallel. Okay, so what we see here is an interesting picture. For example, I like to invite you to look at special structure. So given point, we have three lines. Okay. And there are three lines passing through it. And then, so start from here, here, and go horizontal line, and go along vertical line, and transverse, horizontal, and vertical. So then we can come back to, starting from any point with any center, so we can come back to the original place. Okay, so all hexagons are closed. Okay, so by this reason, so this structure is called hexagonal. Okay, Or on a more modern terminology, so this is flat in some sense. Okay, so later I like to introduce the connection, affine connection. And this hexagonality corresponds exactly to the flatness of the affine connection. Okay, so second example is more basic too, but more deep. Okay, example 2. Let C be a Riemannian surface. Surface of genus G. Okay, and the integration curve, okay, is defined from C to CG. Okay, I'm forgetting a period. Okay, so we like to think about just the local structures, so forget about the period. So definition is take X, then the image should be integration from some base point on the curve, so it's not interesting. Okay, so from base point to X, and integrate one form, holomorphic one form, omega 1, and so we apply the integration to omega g up to, okay, take some base, linear base of holomorphic one forms. And, okay, and of course this is just a space curve. Structure is less interesting, but more interesting thing is the Cartesian product of, say, G minus 1. So this is a mapping of from the Cartesian product, okay, G minus 1 times Cartesian product of Riemannian surface, and to this G space. Okay, definition is the same. Definition is the same, and take point x1 to x G minus 1. G minus 1. Then the image should be, okay, the image should be, say, from star to xi, and takes all summation from 2g minus 1, omega 1, okay. And the second factor is the same, xi, but instead of omega 1, so use x omega 2. Okay, so by this way, we get in a kind of surface in the G space. Okay, this is a hypersurface, codimension one. And by definition, this is just a translation of this space curve. Okay, because I like to, so you will see immediately. By definition, this is image of x1 plus, okay. So this is just in a linear space. So we can make addition x2 plus and so on, xg minus 1. So this way, so we get in a surface, but the surface has structure, very special structure. So I like to tell you the structure. Okay, for simplicity, to visualize everything, so let's assume G equals 3, okay, 3 non-trivial, but the simplest case. Okay, so okay, here we have the 3 space, okay, 3 space, and here this is let's say 0, and the curve grows from 0, okay. This is our image of integration. So I denote, this is kind of an abbreviation. So image I denote by C, the same C, because we can identify naturally. So okay, so okay, so take this point x1, okay, and take x2 here. So then, so we make summation of these two vectors, okay, x1 here, x2 here. So we make sum. So where we go? Somewhere here, okay. We have some. If we vary x1 and x2, so then we have 2 parameters, okay. So fix one parameter x1 and just vary x2, just only one parameter. So then we get just a small piece of curve, so which is just a translation, exactly the translation, parallel translation of this small piece. But if we perturb a little bit x1, okay, then this curve is translated in another direction along this curve, okay. So say if x1 moves in this direction, so then this curve, small piece, is translated in this direction. Okay, so here we have surface, but the surface has two foliations. Okay, so this is the special structure on this surface. Okay, and classically it is known that this surface is the image of integration g minus 1 is the Riemann's theta divisor on the in the how do you say Jacobian space. Jacobian. Okay, dimension is of course g minus 1. Okay. So in general, such a translation surface obtained from such an integration of one form, homomorphic one forms. So we have a foliation structure, but foliation structure is not unique, so it is multi-valued. So it is our web structure. Okay. Okay. So for example, I like to invite you the Abelian theorem. So this tells if x1 plus x2g minus 2, okay, the degree of canonical divisor, okay, then integrate. Then this is always 0, of course, up to modulo period. Right? So this tells to 1 point, okay, to specify, to get 1 point on the Riemannian theta. So we need, for example, in this picture, we have two parameters. We can use just half, okay, g minus 1. We can use just half of divisor, okay. So, oh, sorry. So this, I suppose this is the canonical divisor, okay. Canonical divisor, okay. And to specify 1 point, we need just half of divisor, say k over 2, okay, over square root of k, okay, canonical line bundle. But also by this relation, the same point is pointed by another remaining g minus 1 divisor, okay. So this tells, so I cannot explain more precisely, but this gives us just a very rough idea to get another foliation, because we have the g minus 1 foliation here by using this way, okay, given g minus 1 point and make summation. So then we get hypersurface here. And by using such parameter, so for example here, x1 is parameter, x2 is parameter, x g minus 1. So we have g minus 1 parameters. So it is enough to parameterize points on Riemannian theta. But here we have another possibility to get the canonical parameterization. Okay, so this way we have another foliation here. So this tells, so on Riemann's theta, we have 2g minus 2 web structure of codimension 1, if you like. But the structure is more complicated. Okay. So this is our non-trivial example. And starting from this structure, Poincaré proved Torelli, I don't know, Torelli theorem. Okay, right? And by looking at picture, one can tell many things beyond Torelli theorem. For example, okay. So it's not our point here. Okay. Example 3. So this is our subject. F, x, y, and y prime equals 0. Okay, this is differential equation of first order differential equation on C2. Now here C2 is just an x space and y space Cartesian product. Okay, so here we have something solutions, and the foliated plane, xy plane, is foliated by solutions. But the foliation, okay, but it's not foliation, really a foliation. So it is web structure, because I can, you see, this is, here is web, because solve f equals 0 as y prime equal f1 x and y, okay? And also, so this, for example, this is a polynomial in y prime. So then we have many, finitely many solutions. Y, f1, f2 of xy, and up to fd xy, okay? For each foliation, for each I, okay? So we have, for example, one form minus fi xy dx, right? So this is equal 0. So this defines foliation I, but of course we have defoliations. So we get inside here, so we have defoliations, deconfiguration of foliation, curvilinear foliations. So here, d-web. So what so we can do here? So perhaps it's, so I should remind you some historical results by Riccati, Hooks, and Poincaré, and Painlevé, and after many people. And the idea is, now this is classic. So classic idea is something follow. Okay, assume foliation, but so foliation may have an envelope like this one. Okay, envelope curve. So assume solutions singularity of web structure is only in a web envelope structure, simplest envelope structure. So this is, for example, the good assumption to start. Okay, so here is envelope, and here is another envelope. Okay, and envelope curve might have a singularity, but still, you see, so each solution can be smooth, and all solutions do not have movable singularity, moving singularity. Okay, so in this case, so we can do something, because for special x0, okay, special x parameter, so foliation may have simultaneously very bad singularities. But forget about such foliation, so such bad points, finitely many bad points. So then, given a generic point, take vertical line. Oh no, sorry. So vertical line y, and also, and here p space. Okay. So for each point, so we associate y p plane. P stands for y prime. Okay. On the yp space, this definition, this equation defines a Riemannian surface. Okay. Here, so we have a Riemannian surface. Okay. And our assumption, this tells an foliation wave structure can be lifted to the Riemannian bundle here in a nice way. Okay, and one can discuss what is monodromy and what is, how do you say, return mapping, Poincare mapping. Okay, so this is just a generalization of Ricatti's work. Ricatti, WC, Ricatti. And after Ricatti, Poincare, and Fuchs. And after, Painlevé came. He came and he had somehow generalized this idea. Okay. So, but here, so we assumed that all singularities are, how do you say, there is no movable singularity. So, but in general, one ought to admit movable singularities, because I like to tell you a generic picture. For example, so say, let's think about the surface defined by x, y, and p equal 0. So this is the space in xy p space, surface in xy p space, okay? And if f is, say, generic in any way, okay? So projection here is like a Whitney mapping, okay? Here, downstairs, we have cusp singularity. This is, say, in other words, so this is discriminant. Discriminant in y prime, okay? So when we regard this equation as an, say, for example, equation in y prime, so then the critical value set is discriminant. Okay, and on this surface, so we can think about the contact form omega. Of course, omega equal dy minus p dx. And this equals 0, for example, so if p equals 0, so then this line is just a horizontal line. Or, I mean, lift suspension of horizontal line. And if p moves a little bit in the vertical way, so then p, this line, this direction is rotated in positive direction, positive way. Okay. So this is contact structure. Okay, hyperplane field, non-integrable hyperplane field. Okay, and this contact plane field cuts a line field. Okay, by intersection defines a line field on this surface. Okay, so for example, for simplicity, assume this is smooth. So then, on this surface, we have a vector, one-dimensional foliation, something like this. Okay, so but here, okay, curve is passing through on this singular point, critical point of the projection. Curves is when we are moving on the upper side, and so assume we go down to the different seat. Okay, so then on this at this moment, so when we pass through the singular point, so we have to look just down, straight down. So this means, so curve is just looking down. So then projection of such solution becomes singular to form a cusp. Okay, so this way, if we take a generic differential equation, so then we ought to admit, we ought to have a moving singularity. So we have to do something with movable singularity, right? So then the idea is Perhaps you know many different ideas with each other, but I would suggest that web geometry, web structure here. Okay, so what is web structure? Three web. Say defined by omega 1, one form, omega 2, of course, one form, omega 3, one form on C2. Okay, and assume omega 1 plus omega 2 plus omega 3 equals 0. So this is normalization condition. Okay, so because space is dimension 2 and we have 3 forms, so we can have one relation, linear relation. Okay, starting from this setting, so one can find one form, theta, such that d omega I equals theta wedge omega I. This holds for I equals 1, 2, 3. For all three, we have just one equal integrating factor. Okay, and d theta was classically called Blaschke, right? Blaschke curvature. Blaschke curvature. And, okay. So, I like to tell you the meaning of Blaschke curvature. And, okay. So, okay, so theorem. Say, for example, assume d theta equals 0. This is the flatness condition. Okay, d theta equals 0. So then, theorem and proof. And proof. Okay, so we play some game. Okay, anyway. So then what we can do, so of course, by this closeness condition, we can integrate theta. Okay, and if you like, we put on the exponential and divide omega 1 by this integrating factor. So still we have a relation equals 0. Okay, but good thing here is such a new one form is closed. Okay, so we can integrate. Then we get a function, right? So here we have function u1 and u2 and u3. Okay, and by this relation, we may assume this is 0 identically. Okay, this means the hexagonality, flatness of the three web. Because, you know, so if we introduce this as a, say, coordinate x, y, so z, okay, so this is exactly the same relation as the elementary triangle picture, Melanus, Cheever, Zach, and, okay. So this implies web structure, web is flat or hexagonal. Okay, so now I should introduce connection definition. So one can present this equation as more, in the following more interesting way: d1 omega 2 omega 3 equal theta 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 0 0 0 0 0 0 and wedge omega 1 omega 2 omega 3. And perhaps so you can put some, you like to put some torsion part, but so here we don't need torsion. Okay, but this looks like a defining equation, structural equation of affine connection. But we are working on this 2 space, but this looks like a connection on 3 space. So I can explain why. Because, say, for example, assume omega I equal d u I. Okay, for example, this is the stupid case, but anyway, let's think about it. But so we don't assume. Okay, sorry. So so the idea is, for example, if one forgets one line, so then we get the structural equation of 2 space. And of course, by forgetting, there are many 3 ways of forgetting. So in principle, we ought to have 3 different affine connections. But by some virtue, so we have one unique affine connection. Such unique connection is called, this is called Chern connection. So Chern, when he was very young, he visited Nebraska and he started web geometry first. And after Braske, Chern defined the connection because Braske didn't work all his life, all through his life. He didn't work any connection curvature. He just used curvature. Okay. So the meaning of Chern connection I would say this is just both connection. Because this is nothing but the integrability condition. But at the same time, this is defining equation of both connection of transverse foliation. But by using that idea, so we extended this both connection of normal bundle to affine connection. Okay. So here, say, for simplicity, we may assume omega 1 is dx, and omega 2 is dy. Omega 2 equals dy. Okay? And the problem is the third foliation, omega 3. So one cannot expect a third foliation in special case. Okay, so now, so we like to seek the meaning of both connection, Chern connection. So here, at one point, okay, so let's think about the triangle, okay, and at this point, so we choose coframe, but instead of coframe, so I like to see very small triangle surrounded by 3 leaves, very small. This can be used and instead of coframe, okay, instead of fixing one particular coframe. Okay, so now, so we like to see, so when we translate this triangle to somewhere else, so for example, in this case, so when we translate this triangle to some here, for example, then, so we see, so we can use this transverse dynamics because Chern connection is the extension of both connection. We ought to keep the thickness, okay? So, and we translate. And if this big is determined, so then triangle is uniquely determined. Okay, by this way, so we can extend so this translation to linear mapping of tangent space here to tangent space here. Okay, so by we apply the same idea, we translate this triangle here, down here. So then we get unique triangle, and we can extend to linear one, and come back. Okay, so if we come back, so then we expect to come back to the same triangle, but there is no reason why this point here and this point here, they have the same level, vertical level, because, so this is non-linear. Vertical and horizontal one are linear, but the transverse one is non-linear. So we cannot predict what happens. So when we come back, okay, so we come back anyway. Then we have different triangle here. So the meaning of the Blaschke curvature is just a multiplier of the similarity. This red one, this is theorem kind of statement. This big one is just a multiplication of theta, d theta, integrate on the triangle, okay, triangle here, and the integrate the curvature on the triangle, and put to exponential. Okay, this red triangle is just a multiplication of small initial triangle by this constant. This is the meaning. Okay. So now, let's look at singularity. Singular point set. Okay. So here, this is moving singular locus. Okay. And the third position is somewhere transverse. Okay, and perhaps transverse here too. So, but forget about it. And here, so we fix triangle. Okay, something like this one. And we translate here. I don't know, so what this triangle will be. So, but somewhere very peculiar. And, okay, and go around and come back. So then what happens? So because this is just a double point, so when we go around one time, so then we get the result is just in a transposition of two curves. Okay? So then this direction and this direction is transposed with each other. So it means if we go around and come back, so then we get a kind of a similarity and also transposition, involution. Okay, so something is concentrated here. So in general, so we can expect the curvature. What is curvature here? Curvature is, of course, by definition, and d theta, 0, 0. Okay. So, so here we are using very singular coframe, omega 1, omega 2, omega 3, because the coframe degenerate. So here is omega 1, so here is omega 2, and omega 3 is non-singular one. Okay, so, but coframe degenerate. So, okay, we have something here. So curvature ought to be this form, something basic one, plus some, I would say, residue concentrated on the discriminant. Okay. So, few years ago, Alcides Linsneto, he visited my office for 1 week or 2 weeks. And every day I had a lecture, and we calculated, and we tried to calculate this term, okay? And after coming back to my lecture, so he did 1-page calculation, and I went to another lecture and come back. And in 1 or 2 weeks, finally, we get a formula, kind of formula for this theta, okay? So which is very curious. So before giving the curvature formula, so let f x y y prime equal something the following form: y prime third. Okay, in order to get the 3-web structure, this equation ought to be multiplicity more than 3. But for simplicity, I b y square plus c b x y y prime plus c x y, where all such ABC are holomorphic, or possibly melomorphic, but okay, so it's not important. So if A is holomorphic, then so one can reduce this equation is equivalent to the following normal form, plus one can kill the first term A, and just an equation is just plus or minus C equals 0. Okay, so this is our normal form, the smallest normal form. Okay, for this equation, so we calculated this one. Okay, then the answer is, what is d theta? D theta equal, very interesting, 1/6 of logarithm discriminant. Okay, of course, discriminant is 4b third plus 27 c square. Okay, and plus some residue. I mean, this residue is very complicated. Not complicated, too much complicated, but it's interesting part, very interesting part. X, y, dy, dx, plus, psi. Okay, forget something in this form. And phi and psi are kind of polynomials of b and c. And take derivation. Okay, so this part is some subtle part. So I would call this is also residue. Okay, for special case, for many cases, so this part vanishes identically. So we get just a logarithm term. Okay, it is interesting. So by solving, by looking at this, so we found something very special. 15. Thank you. Say, look at the generic ODE. As before, the projection is like Whitney mapping, and we look at just downstairs, okay? And here, discriminant. And for generic mapping, as you know, this is cusp. Of course, D is defined by delta equals 0, defining the equation of discriminant, right? And solution are all something like this one. Okay, so this is generic picture. generic picture. All generic differential equations look like this one. Okay, so but inside, by looking at, so we cannot detect any difference. Okay, all look the same, but this equation is very important because, for example, light, right? And so when we discuss investigating light and intensity along nearby caustics and phase and so on, so always we use the phase line, okay? And inside the caustics, so phase line, they become multi-valued, more precisely 3-valued. And inside, so we have 3 phase, D1, D2, and D3. Okay, this defining web structure is given by just D equal const. So, but inside we have 3 phase multi-valued function. So we have to do something. We must understand because this is very important. I think because now I cannot convince you by telling Schrödinger nonlinear Schrödinger equation and so on. So, but perhaps you allow me to go on to talk on such a generic 3-web structure. And for such a generic structure, so d theta, so we know has, by using that formula, pole of order 2 along discriminant. Okay, so the reason is here. Oh, sorry, xy, and put dx dy. Okay, this ought to be 2 form. I'm stupid. Okay, so logarithm delta and derivation by x and y. So then we ought to have. Okay, and also this is very elementary fact. And also d theta vanishes on 2 curves. Union of 2 curves, C1 and C2. And C1 is tangent, and C2 is transverse and smooth. Okay, so this tells, okay, and in real picture we cannot see such a component, but inside, anyway, inside there is just one special line, a special non-singular curves on which curvature vanishes. But curvature vanishing curvature, d theta equals 0, for example, say identically 0, this implies affine structure, as you saw before. And it means on the infinitesimally small neighborhood of such a curve, so we have canonical affine structure, and on which wave 3 phases interplay some very interesting resonance. Okay, so this is the reason why, so I would say this is quite important. So I like to call those curves resonant Nant curve. So for generic differential equation, we get a resonant curve. And if we look at the different differential equations, so then we get another resonant curve. And the resonant curve structure is peculiar to a special family. Okay, for each family we get this special direction, special curve. Okay. So this was quite surprising. So on the other hand, more interesting, mathematically interesting problem is to classify flat differential equation, flat one. Flat singular 3-web. So I like to finish my talk by showing classification theorem. So this idea is very closely related to the Alcides Linz Neto, his talk on the Monday afternoon. Okay. And assume, say, let's recall again, surface defined by x, y, p equals 0 in C3 space, x, y, and p. Okay. And so what is the first integral? For simplicity, I like to use the first integral. And the first integral is mapping function from S to C, okay, such that d lambda wedge contact form dy minus p dx. This vanishes identically on S. Okay, so this means they are just linearly, proportional with each, just in a scalar multiple. Okay, this means solutions, the set of solutions is given by projecting lambda equal constant, say t, okay? Lambda equal constant defines a curve on this surface S, okay? On the Whitney surface, okay? So here, and the lambda is defined on this upper space, and the lambda equal constant defines a curve. Okay, by projecting down to xy space, okay, we get solution. Okay, so this definition means just the solutions are given by such projecting. Okay, and in this case, define incidence surface V by the set of those alpha, beta, gamma in C3 space, for which, okay, I write this as a solution parameter with parameter t. Okay, so for example, solution, one particular solution is something like this one, and this has phase d equal t. Okay, so this is that particular curve. Okay, and for which d alpha intersection d beta intersection d gamma is not empty. Because now for each two, of course, in general, no intersection is not empty, but for three, so for generically this is empty. But okay, so anyway, this define this. Okay, so this has dimension 2. Why? Because so we use the intersection. We denote intersection point by x and y. We can choose any x and y, and we can count 3 phases: alpha, beta, and gamma. For example, this picture, we stay here, and waves comes from this direction, and we observe first phase d equals alpha, and we wait, and we see different wave, the second wave, and we observe the second wave beta, and also, okay, so we get 3 waves at each point. So we can choose any x and y. So this variety has dimension 2, surface, hypersurface in C3, and on which 3 wave is defined. V2 defined by d alpha equals 0, d beta, d gamma. Okay, and if the structure here is hexagonal flat, so then structure on V2 should also be in a flat, because, right? And so we ought to classify such a flat variety surface in C3, okay, C3, and define 3 wave is defined by just the first coordinate, second, and third coordinate foliation. Okay, here is classification, and think about V2 and make quotient. Okay, And here, assume here is finite to 1 mapping from C2, okay, or universal covering in Aristoteles Linz network's terminology, universal covering. So the problem is when, so this admits such parameterization, because at each point we get 1 point on the variety, but not this xy defined 6 points on the variety, because so we cannot choose the, how to say, permutation. We cannot fix permutation. So the point for each x and y, okay, starting point, so we can fix 1 point in the quotient space. So the problem arises here when quotient space admits such a universal covering by C2. So of course he knows, but the result here, so we need is more, we need more precise, strong result. The answer is, okay, V must be Fermat, x alpha plus y alpha plus z alpha equals 0, homogeneous Fermat surface, and alpha ought to be 1, 2, 3, 4, and 5, and also 1 over 2, 1 over 3 plus minus, and 1 over 6, and 2, 2, 2, 2, 1 over 2 over 3 plus minus, and 3, and so in my abstract I showed. Okay, so there are finitely many possibilities, only finitely many. For each one, we can take normalization, and on such an xy space, so we can get the flat equation. And just a few hours ago, so I noticed, so I calculated all such differential equation, and the first one, second one, it's okay, but the other things are not so human, too huge, and so. Okay, all flat things are in a pullback of such masterpieces. But so really, real masterpiece should be theorem exist an invariant three web, singular web on C2, but invariant under the polyhedral group acting on C2, right? Polyhedral group. And such differential equations are all quotient of such masterpieces here. Okay, so but here just a few hours ago I noticed and I realized, and so yeah. Anyway, so here we have masterpiece for flat. Okay, I finish.
Thank you again.